All right, like with all the other functions, naturally, if we can find the derivative of them, we should be able to find the integral or the primitive as well, right? And the way I want to do that is I'm going to just start off by refreshing us on our normal trig derivatives, right? So the integral, so I'm confusing myself now. The derivative of sine of x, for example, that becomes cos of x. The derivative of cos of x becomes negative sine of x. And the derivative of tan of x is a bit of a it's a bit of a cowboy. Just kind of disregards all the other ones. Let's just go to sec squared, right? So at this point, again, just by reversing that, we have the identities we need for the integrals, right? Okay, cos becomes sine if I integrate it. Sec squared becomes tan x if I integrate it. This one over here, though, negative sine of x, what we'll tend to do is, okay, if I want the integral of sine of x, that will become negative cos of x, right? So, because if you think about deriving negative cos of x, that would become negative sine of x, and these kind of cancel out, so you just get left with sine of x there, right? So those are the kind of standard forms that we're working with. If we just go backwards, we get our standard forms of the integrals. What I'm going to do is I'm going to write up the integrals now with a bit more variety in the function. So the general form of this. So if I take the standard integrals now for, let's start with sine of x. And I'm going to do sine of ax plus b. So now we've got something in the function, and that's going to become 1 on a, well, negative 1 on a actually, cos of ax plus b plus your constant. Okay, so where's that coming from? Well, that's coming from the fact that, hey, I want to undo the fact that when I derive, I take the derivative of this and multiply it by what's at the front, the coefficient, so these will kind of cancel out. And also because when I take the derivative of cos, it becomes negative sine, so these will cancel out as well. I'll get left with sine there. Now, same thing as the exponentials and logs, like this inside part, that never changes there, right? When you're integrating trig functions. So let's have a look at another one. Integral of cos. And it's the same idea, right? What I'm expecting to get sine. So if I integrate that, I'm going to get 1 on a to address the fact that now there's something inside the brackets. Sine of ax plus b plus any constants. And anytime you see sec squared x, or in general form ax plus b, we can get 1 on a sec squared. Oh, sorry, 1 on a 10 ax plus b. And then any constants there too, right? Awesome. So I guess the biggest trap for students is just to remember what operation you're actually trying to do. Are you trying to integrate? Are you trying to differentiate? Make sure you don't get mixed up between the two. Just pause and think for a moment what you're actually trying to answer here, because time and time again I see students mixing them up, particularly because we learn them so close to each other, right? So we want to find the following. So let's look at finding some integrals. Let's go ahead and find something like this. Cos of x plus sine of x. Right? So this one here is our standard form. So I'm thinking, okay, what's the integral of cos of x? That just becomes sine of x. Oh, sorry. Wrong pipe. Okay, cool. Sine of x. What about the integral of sine of x? Well, and that just becomes negative cos x, right? So that's negative cos x there. And of course, because of an indefinite integral, we have our constant as well. So don't forget that one. Capital. Cool. What about another one? What about something like this? Now remember, if I have lots of terms going on, I can always treat them separately. So that's not a big deal if I have lots of these terms here. So let's look at our form. Okay, the integral of sine of x, that would just become negative cos x. And here, these are like typical functions that you're used to integrating, right? This would be 5x cubed on 3. And what about this one? Yeah, it would just be x or 3x squared, because increasing 1 to the power here, all divided by the new power, sorry, which is just 2, all right? And again, we have our constant, and you can always check the answer by differentiating all of these to make sure we go back to the beginning here. And let's start putting some like numbers in them now, right? Inside the functions. So what if I took now the integral of cos 2x? Okay, so I'm thinking, okay, it doesn't fit any of the regular forms. I'm going to go have a look at this one. I'm looking for cos. I'm thinking here, what's the a value I've got? Well, the a value I've got is 2, right? So I'm going to go ahead and integrate that. My a value is 2, so it's going to go 1 on 2. And that's going to become sine. And I keep the original function the same, it's 2x. And then you have any constants that you add on. All right, so all I'm doing is I'm identifying now, okay, I've got an a value inside my function. And that's going to become a denominator when I pull it out there. We haven't done sec, so let's work with sec squared. Let's do sec squared 5x minus 3. All right. So if I'm going to integrate this, again, same thing. Do I have an a value? I do. That's the coefficient of x in that expression. So it's going to be 5 in this case. Again, we don't have to really worry about that 3 part. That's just to recognize that it's there. So it's 1 on 5 tan 5x minus 3 plus any constants. Now, sometimes they'll try and trick you and they'll do stuff like this. So let's incorporate some more elements to this. Let's say I've got the integral of sine, or 3 sine, let's do x on 2. Yeah, that's an interesting one, isn't it? Okay, cool. So what's different about this one? Well, first of all, we've got a constant here. Like I've always done, I tend to bring constants out so I don't really have to work with them. So if I take that out as a constant from the front, that makes my expression a bit easier to work with. So I'm only worrying about this one now. The other thing is, what's the a value in this case? If you think about it, it's not immediately clear, but if I rewrite this differently, you might be able to tell. The a value, just for an a, sorry. The a value is just half, right? The a value is half here. So if I want to do this using that formula over there, what I have to think about is, okay, the 3 can stay there. What are you going to multiply by then? What I'm going to multiply is I'm multiplying by 1 over that a value, or the reciprocal, right? So the reciprocal of that, or 1 over 2, right? The reciprocal of that, if you're flipping that fraction, it just becomes 2. Okay? So that's something that's a bit different because the a value is a fraction, but we can still approach it in a similar way. And then I'm going to get negative cos half of x plus any constants. So I'll just get negative 6 cos of x, half x, sorry, plus constants. Okay. And I can give you one more. Let's do something like this one. And I'm trying to identify my a value. All they've done here is they've just said, all right, well, the a value is negative 4 in this case. They've just rewritten it slightly differently. So I'm going to write that as 2 times, when I integrate, 1 over my a value, 1 over negative 4. And then that's going to become sine when I integrate using my form over there. The original function stays the same though on the inside. And I just get left with negative half sine of 4 minus 4x plus my constant value, okay? So that's how I can approach these kind of problems where I have to do indefinite integrals.